Very good evening and wishing you all a very happy Diwali and welcome to my channel Physics for Students, where in today's lecture of quantum field theory what I'm going to do is that I'm just going to give you a very quick understanding on a topic which I was been talking about, that is limitations of classical field theory in terms of explaining a certain phenomena of physics and why it has got a limitation, number one. And due to this limitation, what we are learning, that is, we are evolving into a new field theory, which is called a quantum field theory. So first, we need to understand what is the limitation. And this limitation actually causes due to it is unable to explain one particular phenomena, which is called spontaneous emission. So I would like to show you in a few slides what it is, because this is very central in understanding the evolvement of quantum field theory, because without the understanding of this, it becomes difficult, or we would say that it is not always in a smooth pattern to understand that. So first of all, we need to understand the limitation of Schrodinger equation, which is the central, I would say, pivotal force of quantum mechanics, and thereby what is the limitation that it has. Now, first of all, I would like to show you what is a spontaneous emission. Here, quickly, you can see on this slide what I have tried to explain. This is a very, it is a very, I would say, easy phenomena, a natural phenomena. So it is basically responsible for all the lights that we see. So you can see that it transits from an excited energy state to a lower energy state. So it emits a quantized amount of energy in the form of a photon. Now, when I say that it emits a quantized amount of energy, that means from the higher energy state, when the photon, when the excited atom goes to the lower energy state, there is a problem. It emits a photon which goes from higher to lower energy state, and this is known as what is known as spontaneous emission. Now, this spontaneous emission is actually responsible for all the light that we see around. So let me give you some practical examples, and then we will understand what is spontaneous emission, and then we will understand that due to this incapability of Schrodinger or classical equation to describe spontaneous emission, we are going to quantum field theory. So here you can see, as I have shown here, fireflies. You know what are fireflies? This is quite common. So fireflies produces light through a chemical reaction that takes place actually in their abdomens. So this reaction excites molecules in their bodies, and then they emit a photons, which is known as bioluminescence, because it produces due to biology. Neon lights, as you see, are filled with neon glass, which is excited by an electric current. So this is also a phenomena of what is called spontaneous emission. So the excited neons atom emits photons of light, which gives neon its characteristic to glow. LED, for example, light emitting diode, they are semiconductor devices that emit light when they are passed through an electric current. And that the light is absorbed by recombination of electrons. Incandescent light bulbs produced by light by heating a filament to a high temperature. The filament glows, which gives the light bulb its characteristic glow. Now, what I'm trying to give you is that these, as you have see, these are actually the process occurs and is responsible for various life in a natural phenomena. Now, as you understand that these are actually natural things. These are natural things. These are, something which is happening all around the nature, and that is what it is called spontaneous emission. Now, let us understand spontaneous emission again comes of three types. The first one is basically what is called luminescence, coming from the Latin word lumen, which means light. So if the atoms are excited by some means and others than heating, the spontaneous emission is called luminescence. Fluorescence, because the excitation is affected by the absorption. So one is the emission, one is the absorption. So absorption is the fluorescence, excitation is luminescence, and sometimes molecules have a very metastable level and it continue to fluoresce long after the radiation is turned off, and this is called phosphorescence. So figurines that glow in the dark has got a phosphorescence. So these are various types of spontaneous emission. Now you might be wondering that why I'm telling you, because once we understand spontaneous emission, the other things becomes easy. Now there is a question that who first observed spontaneous emission. Now, it is none other than our dear old Dr. Albert Einstein, as the, this APS, the Advanced American Society, they say that basically it is through Einstein's works that we first came to know about the spontaneous emission. And as you see, this spontaneous emission sets the scale for all radiative interaction, such as absorption and stimulated emission. That means that this is basically the base, the spontaneous emission, and from here all the absorption, etc., takes place. We will come to a common misconception which also happens. So here you see in the slide that the atom stays before an excited state, then it drops down to the lower energy state during this process it emits what is called a photon. This emission of photon actually cause all types of disturbance. I mean to say, now we are going to study that this emission of photon takes place, and there are certain degrees of infinities which happen, which the classical field theory is unable to explain. Now, because classical field theory is unable to explain, we need obviously a new theory. So that is why we first understood what is a stimulated emission. It is emission, absorption, as well as fluorescence, and it was Albert Einstein who first observed the spontaneous emission. Now you see, here is a common misconception, that is spontaneous emission and spontaneous radioactivity the same? Absolutely wrong. Because understand that it was Henri Becquerel, husband of Marie Curie, Henri Becquerel, yeah. So he actually discovered what is known as radioactivity. It is around 1896 that he found that certain substances like uranium emitted radiation without an external stimulus. So from what we understand is that obviously spontaneous emission and spontaneous radioactivity are not the same. Because spontaneous emission is the process in which an excited atom or molecule emits a photon, and it does not require any external stimulus. Spontaneous radioactivity, on the other hand, is in the process in which an unstable atomic nucleus spontaneously decays, emitting radiation in the form of alpha particles. That means here is the difference. One is that it is emitting, another is one, it is decaying. So obviously both of them are not the same. Now you need to understand, here I have written something very important, that this spontaneous emission happens without any external stimulus. Now what do we mean by external stimulus? That means a particular photon is being emitted without an extraneous intervention with that. That means spontaneously is emitting. It is simple, like in English language when we say, spontaneously good poet, spontaneously good batsman, that means it is coming without any external interference. And that is why it is called spontaneous. Radioactivity, on the other hand, is not spontaneous. It is something which is causing a decay, and as I have explained earlier, that it causes alpha, beta, and gamma particles, and then it is later united through electroweak unification through Abdus Salam and Steven Weinberg model. Anyway, that is a different story. What is important is that because it is causing without any external interference and it is happening spontaneously, that means without any intervention, the photon or the emission is done. Now, if without any intervention an emission is being done, classical physics always deals with events which has got interaction, momentum, particles, whatever. Now, how can we define a system or an emission of an atom or any subatomic particle which is spontaneously happening? That means there is no, even in the vacuum, electromagnetic field, without anything which is coming in between, the emission is happening. Now, remember, classical physics cannot actually explain those things, because classical physics needs particles, fields, something like that, which would actually describe the phenomena. So if it is spontaneously emitting, if it is in a vacuum and without any intervention, then how come classical physics define it? Because as we know, classical physics does not have something which will define things without any external intervention, because it needs medium through which classical physics can define. That is the basic idea of spontaneous emission, and what we call is the limitation of classical physics. So here is a quick understanding. Remember that spontaneous emission and spontaneous radioactivity are not the same. I've given this is excited atoms. This is unstable atomic nuclei. This causes photons. This causes alpha, beta, and gamma particles. This has got no external stimulus. This has got also no external stimulus. This is the fundamental concept in quantum physics. This has got absolutely no relation to quantum physics. We will see later in our series that it has actually got to something with the decay, and this decay is basically happening due to weak interaction. We will take it up later. Now here comes the most important point, that why classical physics cannot explain spontaneous emission. Now here you see from the basic definition, look at the definition. It says that spontaneous emission is the process in which a quantum mechanical system transits from an excited energy state to a lower energy state with a quantized amount of energy. Now this is important. The definition says quantized amount of energy. And as we know that quantization is something which is not done in classical physics. Classical physics do not deals with quantization. Classical physics deal with something which is very continuous. So right from the definition, we got the first hint that classical electromagnetism is not quantized, remember. Because classical physics assumes that energy can exist in any amount, while quantum physics says quanta, that means it exists in quantized amount. Now this not quantized leads to the second point. In the absence of quantized electromagnetic field, the excited atom cannot decay to the ground state. That means, as I told you, there is nothing intervention in between. Automatically the atom or the subatomic particle is decaying. That means it is automatically coming to the ground state without any external intervention. And in order to explain the spontaneous transition, quantum mechanics must be obviously extended to a quantum field theory where the electromagnetic field is quantized at every point in space. Now here is a point. Earlier, if I take the books of which is up there, which I take the books of classical field theory, you will see that there is a term which is called canonical quantization. I won't talk about this because that would demand a separate lecture. Canonical quantization is something where classically electromagnetic fields are quantized. Although canonical quantization again cannot define spontaneous emission. So because quantized amount of energy is dealt with, obviously classical physics cannot define quantization. Classical physics assumes that energy is continuous, which deals with the absence of quantized electromagnetic fields, and which deals, in order to explain this kind of a spontaneous natural phenomena, we need to have electromagnetism to extend to certain thing where each and every point in electromagnetism and quantized, and spontaneous emission is an irreversible process. That means it cannot go back to time. Although if you see, I will just show you an example in thermodynamics, etc. We have something which is reversible process. That means theoretically, if the cup is falling down from the table, with the arrow of time, we can come back and we can assemble and get the complete cup. This is called a reversible time process, which thermodynamics and other areas of physics we know. But this spontaneous emission is irreversible. Once it is emitted, it cannot come back to the original state. Now this is a question also, why the atom excited from a particular photon excited from the particular nucleus, why it cannot come back to the state? Does it become tired? Does it loses some energy? I will just show you. So this actually shows that why classical physics cannot explain spontaneous emission, because classical physics is not meant for using quantized energy, and for that we need to extend the physics. Next, you see here is something which I would like to show you, that spontaneous emission is generally considered as an irreversible process. So here you see the atom right at E2, that is the higher energy level, is coming down below. That means from E2 I can come back to E1, but from E1 I cannot go back to E2. Why? Because once the spontaneous emission has taken place, the system moves to a lower energy state. The emitted photon carries the energy difference between the initial, that is E2, and the E1. And the emission of the photon is a random event. That means the system does not return to its original state. And as written over here, the process is irreversible, meaning the system cannot go back reversing the process. Now you might be thinking that what is the reversible process? I have given you an example, reversible isothermal expansion. This is where the gases expand or the temperature cools down and again heats up. And again, when you cool down, it comes back to the cold state. Again, heat up. So what is happening? This is a kind of a simple example. Then thermodynamics, etc., we have got reversible processes. The cup breaking down and the cup building up. Again, the cup breaking down, cup building up. But in case of this kind of an event, spontaneous emission, the particle can move from E2 to E1, but again, it cannot go back from E1 to E2. Why? I'm just showing you in the next slide. Okay, here you see. Okay, now I would like to explain you in this case. I will come to the slide later. There are three instances which takes place one by one. Possibility number one, you see on the left hand side, the atom actually emits a photon, right? The gamma sign. Now this photon, this photon, when it is generated, it has many infinite ways or degrees of freedom. That means that the photon has many possibilities. It can go here, it can go here, it can go here. So the probability of an emitted photon being reabsorbed by the same atom is very low. Why? Because I have shown you that this photon has a wide range of possible directions in which it can travel, and only a small fraction of this direction will lead back to the vicinity of the atom. Now, how can we know if there are so many ways it is going this way, this way, this way, this way, this way? Where will ultimately it will come down? So possibility number one is erased because of the infinite, and that is why I have talked it earlier. That is why we need renormalization, because physicists and mathematicians, we cannot deal with something which is so much infinite, isn't it? So we need to renormalize. We'll come to that later. Possibility number one, it cannot come back because the photon has got many directions. Point number two, even if the photon is absorbed by the atom, it is not guaranteed to return to the original state. Why? Because photon may lose some energy in due process of time. That means from my home, when I'm going back to college, running, then in the process of running, I will lose some energy. Then it is quite sure that from the college, I cannot run back to my home. So that is why I have shown that the photon might be it go back to the same atom, but in the process, it will lose up some energy. And losing up this energy that is why it cannot go back to the excited E2 state. So possibility number two is erased. Now possibility number three is that even if a photon has managed to come back, reabsorb, and move to the original excited state, that is E2, remember that the reabsorption process is not instantaneous. What do I mean by that? That means that there is a time delay between the emission of the photon and its reabsorption during the atom, and during this time delay, it can interact with other matters in environment. That is, it is not instantaneous. It takes time, and this time, in the meantime, it can interact between other matter. So the interaction can make it more difficult for the reabsorbed photon to excite back to the original state. So the first is that the subatomic is emitting the photon. It goes in 1, 2, 3, 4 infinite directions. We cannot know which direction it is going. Second point is that it has emitted, and suppose it is coming back to the original state, it cannot, because it has lost some energy. Now, third state is that it has emitted and it has come back to the stage, but this coming back to the stage is not instantaneous. That means it has got many other, what I would say, time delay. So it has interacted with matter and things are lost. So this is the reason that spontaneous emission becomes something which is difficult to gauge by classical field theory. So here you see what happens is that in quantum electrodynamics, the electromagnetic field, remembered, it is not empty. It contains lot of virtual photons. I have explained it in the Feynman diagram. So what is the Feynman diagram shows that in between that there are a lot of virtual photons, this way, that way, this way, that way. So what is happening is that the vacuum or the ground state, that means when it falls down, of the electromagnetic field can fluctuate, creating and destroying lot of virtual photons. So what happens, as you see from the ground state, it goes and interact with the virtual state. And when an atom is in an excited state, it can interact with virtual photons. Obviously, when it is in excited state, it is interacting with virtual photons. And this interaction can cause the atom to spontaneously, because it is interacting with you, me, and many other people, it is interacting. So it is continuously, this interaction actually causes the spontaneous emit of photon. And that is why if there was no photon before, still it emits. So this is known as spontaneous emission. Now here I will now come to the point that why classical physics cannot. I will come with the Schrodinger equation, but I hope you have understood what is spontaneous emission. It is a very spontaneous process, and it was first observed by Dr. Albert Einstein, and it is not the same as radioactive emission, that is a decay, this is an emission. Emission, absorption, we have seen different type of things. Also, what it comes to the point is that there are three possibilities which we have eliminated, and it is interacting with virtual photons. That means without any particle staying in the vacuum, just you and me sitting, it can emit photons. Now here you see that I have shown that there are many different ways in which so you see from the ground state, I have shown multiple arrows which moves to the excited state, isn't it? From the ground state, there are many arrows which are moving to the excited state. And what you see over here also, that there is, but there is only one way in which the atom can transfer from the excited state to the ground state. That means from the excited state, that is the top E2 level, going to E1 level, that is only one state. But the emission, once the photon is emitted, it is very difficult for the atom to reabsorb, because there are so many infinite amount of configuration possibilities that the electromagnetic field could be in. And that is why we cannot mention that. I'm just skipping this part because you all understand that classical physics cannot fully explain time irreversible process. I've just given an example of entropy, because entropy is always increasing. It is an irreversible process, and that is why it loses some energy associated with the surroundings. That is what we are seeing right now. And the classical physics cannot explain entropy properly. So classical physics can describe processes like the spreading of gas throughout a container, or the cooling of a hot object in a cooler environment. That is what. Now here we come to the central part of our lecture today. What is the equation that describes, because this is, we understand this is a quantum mechanical phenomena, and without quantum mechanics, obviously spontaneous emission cannot be observed. Now the question is that what is the equation that was trying to define quantum mechanics? Obviously Schrodinger's equation. But even Schrodinger equation, I told, that is unable to describe spontaneous emission. That means there is a limitation, there is a problem. What is that? And then only we understand why we need quantum field theory. So the limitation is this. As you see, that Schrodinger's equation is something a kind of I can say equivalent to classical mechanics. Like classical mechanics, for example, F equals to ma. If I take the second order derivative also, what it says that given this condition, we can say where the ball will go, the cannonball will fly. That means given certain initial conditions, we will be able to tell how the system will behave. In Schrodinger's equation, it is happening in the same way. Given certain conditions, initial, final, etc., kinetic energy, potential energy, we can say how a wave function evolves. Wave function means the entire quantum mechanical system. So the Schrodinger equation plays the role of, so it was postulated in 1925 and it was published in 1926. So Schrodinger equation gives the evolution over a time of a wave function. That means you can obviously say that Schrodinger equation and Newton's laws of motions are more or less the same. Here also you're given initial condition, the system is evolving. Here also you're given initial condition, the systems are evolving. So the kinetic and the potential energy stands to be the same. Now here comes the problem. The problem is that, let me show you, that the Schrodinger equation itself says that the electron's energy is not quantized. Remember, we are dealing with electrons, and classical electromagnetism, which is called canonical quantization, that is already there. But Schrodinger's equation cannot define or doesn't quantize electrons' energy level. Point number one. Point number two is that electromagnetic field is not quantized. Obviously, electromagnetic field is not quantized. If it would have quantized, then we would have explained spontaneous emission using classical physics. So number one is that electron is not quantized. Number two is that electromagnetic field is not quantized. And now you see in point number three that it is a non-relativistic phenomena. So the equation is non-relativistic in nature. That means it doesn't take into account Lorentz invariance, special theory of relativity, etc. So now you understand why Schrodinger's equation has got a limitation. First of all, it is very classical in nature. I mean, to say classical in nature. Don't think that this is a classical equation. Obviously, it is a quantum equation, the wave function and the partial derivatives. But it is classical in nature. That means given certain system, it will tell what the system will evolve into. But that is not what we are looking. Given certain system conditions, what the system will evolve into, if we know that, we could have explained that by Newton's laws. But here spontaneous emission is what? Spontaneous emission is there are no conditions, but the atom is emitting. Isn't it funny? So there are no conditions given, the atom is emitting. From the higher energy to lower energy, photons are coming, and the photons have got infinite amounts of freedom. So what we need is this one, the very gentle, handsome gentleman, Paul Adrian Maurice Dirac. I hope you remember Dirac actually coined the term boson, that is Bose and Einstein, and fermion, that is Fermi-Dirac statistics. So this is the person, Paul Adrian Maurice Dirac, very, very good looking, a little bit cynical in attitude. He proposed something that no, we need to extend Schrodinger equation into what is called relativistic Schrodinger equation. Remember, Dirac's equation is nothing but the relativistic Schrodinger equation, which was classical in nature, cannot explain spontaneous emission, was taken to the next level, which is called the relativistic equation. Now, when we say relativistic equation, what does it mean? That means it will have special relativity, it will have E equal to mc square, it will have Lorentz invariance, it will have Lorentz boost, everything. Because the basic underpinning force of special relativity is Lorentz invariance. That means all these things were put together by this genius Dirac, and he formed what is known as Dirac equation. So spontaneous emission is relativistic, and Dirac equation is a good starting point because it was taking into account what is called the relativistic part. So this is what I just wanted to tell you. I would be extending today's lecture. So let me summarize from here what we got today quickly. Let me go back to the slides. So first we understood what? We understood what is a spontaneous emission. We also understood, okay, let me go back to the slide. Yeah. So first we understood that what is a spontaneous emission, fireflies, neon lights, etc. And we saw various types of spontaneous emission: excitation, absorption, and phosphorescence. From there, what we found that it was Dr. Albert Einstein who first observed spontaneous emission. We also found that spontaneous emission and spontaneous radioactivity are not the same, because this is actually caused without any external stimulus, and spontaneous radioactivity is basically caused by an unstable atom which decays into alpha, beta, and gamma particles. From there, we found out the differences between spontaneous emission and spontaneous radioactivity. After that, what did we found? We found that spontaneous emission is something which cannot be explained by classical physics, because it says quantized amount of energy, and classical electromagnetism does not deal with quantized energy. And in the absence of quantized electromagnetic field, the excited state atom cannot be explained. Okay, so what is quantization? Indrajit Das is asking. Okay, quantization actually means that okay, first let me answer to Indrajit's question. So quantization actually means that you are actually, say for example, a particular area. I don't have the whiteboard, my mouse is in my bag, otherwise I would drawn and showed. So you've got a kind of a field, right, Indrajit? You've got a kind of a field, okay, and each and every point you are being able to quantize. That means a discrete amount of energy, the incoming, the outgoing, whatever will happen, you are quantizing it. That means you are telling that based on the position, momentum, this, that, what will happen? What is the internal force? What will be the outgoing force? So quantization actually quantifying, that means you are telling exactly how and what it will happen. So the difference, as you see, Indrajit, is that in classical physics, we don't know about quantization because it's all continuous. But in quantum mechanics, the very word quantum actually means quanta. That means certain amount. And you define that amount. So that is what is called quantization. So you can quantize my face, you can quantize my finger, you can quantize anything. That means each and every area you are being able to define that this particle, and whatever it is happening. Right, Indrajit? I hope this is clear. And this is an irreversible process. That means it cannot go back in time. Once it is emitted, done. So this is also what we came to know. The second thing what we came to know is that so this is the same thing. We came to know about three probabilities. One is that if it emits an photon, it goes into many directions. So how will we come to know which direction is going? Probability number one eliminated. Even if it goes back, it loses some amount of energy. Oh, after walking, I'm feeling so tired. So we lose some amount of energy. So obviously, there is a less probability that it will go back to its original state. And third is that even it goes back to its original state, there is a gap, there is a time, maybe few seconds or femtometer or whatever. So this time, in the meantime, what is happening? There are a lot of friends of photons which are coming, which are intermixing, and it is causing a problem. It cannot ever go back. Because if I'm mixing with this, mixing with that, then how can I go back in time? Obviously. And it interacts with virtual photons. So from there, what we come to know is that the limitation of Schrodinger equation is essentially same as Newton's law of motion, because this is given certain condition, it will evolve certain condition. You are also given certain condition, it will evolve into a wave function. The next point, what is important is that the limitation, that is energy level, is not quantized, electromagnetic field is not quantized, and it is not relativistic phenomena. And all this emission, absorption, etc. are all happening because they are all relativistic. Here comes Paul Dirac, who formed the relativistic form of Schrodinger equation, and it actually takes into account all the further details of special theory of relativity, Lorentz transformation, these, that, A, B, C, D, and it forms a nice equation, and that is called Dirac equation. And Dirac equation now can explain what is called Schrodinger equation. The spontaneous emission. So I hope that this is something which I have already explained in the video, but I always feel that talking and explaining things over a class or something is good. So we will continue. Don't worry, we will continue. Maybe not tomorrow or day after tomorrow. Thursday or Friday, I will try to come again online. And till this time, maybe on quantum field theory, maybe I can start with a question answer session, or I'm also planning to something with differential geometry and general theory of relativity, how to learn, what are the books, how to read, what are the best books to go through. So we will look into that. So please do let me know how you like today's short, because I extend more than an hour or so, but this is very important. I hope you liked it. Okay, Indrajit is saying thank you, sir. So Indrajit, is the concept very clear? If the concept is not clear, please do contact me over my email, because this is very important. I am taking you a step by step into quantum field theory, because generally if you jump into all those Dirac equation, etc., it is a big problem, because you really don't understand the background. Once you understand the problems, limitations, background, then learning quantum field theory will become very, very interesting. So I'm trying to build up the base. So it might take 1 month, but how does it matter? We are not in a rush, right? We can build up the base, and then we will go back to the direct equation. So thank you, Indrajit, and those others who have watched this. I will wait for a comment. Please put down some comment. It looks good in the comment box of YouTube. So that's it. Thank you very much, and stay safe and happy, and enjoy your Diwali. And we'll be back, and I have got many plans to come up. Please stay tuned with your Physics for Students, because speakers coming up next Sunday, and next to next Sunday, and next to next Sunday. So all 3 Sundays we have got good speakers. First on is on astronomy, astrophysics. Second person is from high energy physics. Okay. There's somebody from Ottawa, I think Canada, just arrived. Okay, enjoyed the great series. Yeah. So His Highness, you can look into this, because this is very important. You might have missed it. This is a very important topic we discussed. So next Sunday, Professor Abhidub Datta is coming from IIT Indore to talk on astronomy and astrophysics. Next to that, Dr. Debanjan Bose is coming from Satyan Bose Institute. He will be talking on high energy physics and researches and options. And on 3rd December, Dr. Sudeshna Ganguly coming from Fermilab to discuss on G-muon experiment and particle physics. So all these Sundays are occupied. And in the meantime, one Sunday, I have got my free webinar on Einstein general theory of relativity, which I have already announced. That is Saturday. So 19th, 25th, 26th, 3rd. 19th is Professor Abhidub Datta. 25th is basically my free webinar on Einstein's relativity. 26th is Dr. Debanjan Bose. And 3rd of November, Dr. Sudeshna Ganguly from Fermilab. Very important personality. Let us engage in a nice discussion, and we can learn a lot of things from her. Thank you very much, and wishing you a great evening, and may the good Lord be with you. Thank you very much. Goodbye.